You said where do you want zeros to be?
Yes. All right, so there is a place to put 0, x equal to 0, which makes it the math simpler. But wherever you put x equal to 0, we're still going to end up in the same place. It's just a matter of, we have to make an adjustment if it's not in the optimal place.
Let's just put it directly over your point.
So,
2.5.
in the middle here? Good with that, Lawson?
I'm not thinking, last time I picked something like this.
I remember that.
So,
All right, so that's where x is equal to 0. We'll make this distance here x. Unless you want to make the other way x.
It doesn't matter. I do, however, have one more question.
Yep.
If the line was disproportionately to one side, would it be more beneficial to take a point in the center of the line or directly overhead?
Directly overhead.
Okay.
Yeah, the fact that it's the center is not as important as the fact that that's the shortest distance there.
Okay.
This is the optimum spot. All right, so if I look at that triangle, that is x, this is r, and that is 2. That is a right angle. R squared is equal to 2 squared plus x squared. At least the math people have me convinced that is true. So r is the square root of 4 plus x squared. We pop the lambda out, so we have k lambda times the integral of dx over the square root of 4 plus x squared.
Now, when you do this, you're going to the tables at this point, right? Or are you?
Yeah, or the quiz, I think it's one of the equations at the top of the quiz. Yep, there it is.
Because like the one on the master set was like 32 plus 2x squared.
Yeah.
In the denominator. And yeah, I guess you pull out the 2? You pull out the 2?
There's one of the ones I graded who didn't do it, and it's not, you can adjust it slightly that way, but yeah, factoring the square root of 2 out, and then you're left with 16 plus x squared, or z squared,
Okay, so it does become, okay.
and then you go to the tables.
Okay, I just want to make sure that was correct. All right, thank you.
All right, so this particular integral right here, we have a single variable here, so what are the limits of integration?
0 to 5.
No. Because of where you defined x.
Okay.
Sorry, where you defined x is equal to 0, I should say.
Oh, negative 2.5 to 2.5.
Yep. That's the biggest mistake I see students in this position make, is they're so used to going 0 to 5 or some limit to that, but it really does depend upon where you set 0 to be. And so that's k times lambda times the natural log of x plus the square root of 4 plus x squared from 0, now I'm doing it, negative 2.5 to 2.5. Obviously. Which is k q over big L times the natural log of 2.5 plus the square root of 4 plus 6.25 minus the natural log of negative 2.5 plus the square root of 4 plus 6.25. So 9 times 10 to the 9th, not negative 9th, as some people have claimed in the past, times q, which is 4 times 10 to the negative 9, over L, which is 5, times the natural log of 2.5 plus the square root of 10.25 divided by negative 2.5 plus the square root of 10.25. In my head, I'm getting somewhere around 14, but plus or minus 10.
I got 9.154.
9.154. What did we get last time? It was 9 point something.
Yeah.
9.01.
Suddenly picture myself writing the test and doing the first problem that we just did, then going. The other one is lined up directly with the middle. Where would you put it in order to get the exact same potential? That would affect this number right there.
I got a different answer, but
What'd you get?
15.0809.
I got that one.
The 15.09?
Yeah.
Does someone have something that they want to say to Marisol?
My calculator's not working, I don't know.
Marisol, did you want to say something to them besides blame your calculator?
No, not really.
Okay. I didn't know if you wanted to accuse them of being wrong. If we go by majority, if we go by physics by democracy, doesn't always work that way, but doesn't always work well. That was not a political comment, that was a comment about sometimes the majority makes a mistake in physics. Although I think politically, I think both sides would agree to the same comment, doesn't always work.
Yeah, that's a safe one.
Yeah, I need to stop there. Before I go on a rant. All right. Ta-da! All right. Calculus for you. Does that feel good?
Definitely satisfied.
All right. How many of you have heard of the nabla? Nabla. N-A-B-L-A. It's a nice Scrabble word too. All right. The nabla.
Is that named after someone?
Pardon?
Is that named after someone?
I have no idea how they came up with that. I don't think it is, but it's quite possible. Or it started out as some Czechoslovakian name, and by the time it made it over to England, they changed it and consolidated.
For my notes, is this still chapter 26?
Yeah. Yes. Yeah, because 25 was Gal, 20, yeah, this is still 26. So we've talked about the electric field. I'll connect it to the devil in a second. And the electric potential. When you had the negative charge here in the lab and the positive charge here, in which direction did the potential difference increase? Your equipotential lines, as you went this way or that way, did you get higher and higher potential readings?
In the center. In the center.
That in the center? Expecting some very strange results now from what you did.
Closer to the charges.
Closer to what?
To the charges.
So, in the lab, you got a high potential reading here and a equally high potential reading there?
Higher.
Higher than positive.
Okay, yeah. So the potential increased goes that way. I guess the voltage increased also. Which way do the electric field lines go? So the direction of the increasing potential difference is opposite the direction of the electric field. So it's something to keep in mind. So whatever relationship I come up with here, there's going to be a negative showing up. We also have to somehow resolve the fact that this is a this is a vector and this is a scalar, so we need to somehow connect them, and that's where that's going to come in at some point. But we're not there yet. So I know that the electric field is equal to the force over some test charge, some charge that's bathed in that electric field. I'm going to multiply both sides, do a dot product of both sides with some differential of some radial vector. And just bring the 1 over q out front for right now. 1 over q f dot dr. May as well integrate because I got some differentials there. Yeah, let's see if this color pops. Ooh. Now this force involved here is the electric force, so this is a conservative force. So what is F dot dr? Or dx or ds or whatever letter we happen to be using for position? Yep. So this is work. It is conservative work because the force involved in this particular case is a conservative force. And what is conservative work equal to?
Negative change in
So this becomes negative change in potential energy divided by charge. I guess electric potential energy specifically. And the negative change in electric potential energy divided by that test charge is the change in electric potential. So we have a relationship right there between these two, is that the change in the electric potential, otherwise known as the electric potential difference or voltage, is equal to the negative integral of E dot dr, or dx or ds or whatever letter you happen to be using. So we got one relationship right there. I'm going to hand wave through the next bit.
Is this leading into amperes?
Not yet. That's still 2 chapters off. So this right here is the integral of dV from some initial potential to some final potential. Sort of working backwards. So this was one of our endpoints right there. That was one of the relationships. We're going to take that and keep going. So dV is equal to negative E dot dr. And now the slight hand wave because, frankly, dividing by vectors is still something a little bit nebulous, at least in my education. Or, I really should do, there's the value marks around that. So it's a crude derivation, at least the second part is a crude derivation of the other way, of the other relationship there. Now, sort of assumed in one dimension to start with that E and the R are in the same direction, thus like the sort of the justification for getting rid of the dot product and just dividing by dr. But it will at least get to this relationship here. Ooh, lost the minus sign. I'm going to generalize it now. That the electric field is equal to the negative gradient of V. This is sometimes written as, we'll throw the negative sign into it also, grad V. And have you dealt with div grad curl? Those are three separate things. Gradients, curls, divergence. Okay. When you take Calc 3, at some point, if you're in, who's in Calc 3 right now? Anyone? All right, you haven't gotten that far yet. At some point, you will get to this.
I've already taken it.
Okay.
I took it, I didn't see it.
You didn't?
Yeah, I kind of remember gradients, but
I
not
don't
enough
The
to
partial.
tell you what it is.
The partial derivatives coming in.
Yeah.
We did see gradients,
Okay.
but I don't remember.
Okay. It's not required that you remember it, it's just, I just wanted to say, hey, it's coming if you haven't seen it yet by the time you get to Calc 3, especially, I think Calc 3 is required for everything at all that you want to do.
Yeah.
So this, basically, this is known as a vector operator. And the fact that it is a vector, it does have I, J, and K components, but it is not something with a specific length per se. More specifically, the nabla is defined as the negative of the partial derivative with respect to x. Let me write that slightly differently. Assuming I hat in the positive x direction, j hat in the positive y direction, k hat in the positive z direction. So this becomes I hat del x plus j hat del y plus k hat del z. This del x, for example, this is known as a partial derivative. The mechanics of partial derivatives is incredibly simple. It's a lot simpler than the stuff you do in Calc 1. Because with partial derivative, you see what the variable is, x, and that is the only variable. Everything else is assumed constant. So if v is equal to xy, then del v del x is just y. Even if y is dependent upon x, you assume it's constant when you're doing the partial derivative. If y is a function of x, then you cannot do that if you're doing just a straight up derivative. Then, so straight up dv dx would be y plus x times dy dx. That's the normal derivative, partial derivative, a lot simpler. Where do I have some room? So, if my electric potential is defined by the following function, xy, my electric field is the negative nabla of V, or probably better worded, the negative gradient of V. And so it is negative, oops. That negative should not be there. The nabla does not inherently have a negative sign. The negative sign comes from the equation here. So negative I hat del V del X minus J hat del V del Y minus K hat del V del Z. That, as we just did, is Y. So this becomes negative I hat Y. Del V del Y
X.
minus J hat X minus K hat times what's del V del Z?
0.
And so my electric field is negative Y I hat minus X J hat. So if I tell you a coordinate, so if I'm looking at the coordinate 4, 3, meters, my potential is 12 volts. I am assuming that there's some coefficient in here in order to make this work out, make the units work out. And my electric field is negative 3 I hat minus 4 J hat newtons per coulomb. Again, assuming there's a coefficient to make the units work out. I'm going to hand back the chapter 23 quiz and flash quiz. Make sure there's a grade on them. Yes, there is. All of you have had me before, but just as a reminder, with this grade in the grade book, all of your grades, the worst that you can do in this class for all of you is an F, and the best you can possibly do in this class now is an A. The system is set up so that no grade is going to sink you. Now, if you get a 0 on a test, it'll be a lot harder to make an A, but an A is still possible after one test. Probably be halfway through the semester before the first person gets eliminated from possibly getting an F or possibly getting an A. And let me stop this.